Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. In this video, we are going to talk about integrals as antiderivatives. So, in our previous video, we have defined what are integrals via Riemann sums. So, let us recall first what that was. So, suppose f is a function defined on a domain containing the interval a comma b to r. We looked at partitions consisting of points x1 through xn minus 1, where x0 was a and xn was b, and x1 through x2 through xn were increasing from a to b. And then we chose some particular points within each sub interval. So, xi star is a point chosen from xi minus 1 comma xi, that interval. And based on this data, we defined something called the Riemann integral. So, delta xi was defined to be xi minus 1. So, the length of each interval, each sub interval, and the norm of p was the maximum over the lengths of all the intervals in that partition. Then we defined something called the Riemann sum of f with respect to this data that we have. So, this was defined as f of xi star times delta xi, sum from 1 through n. And the idea here was that we were looking at rectangles which had the base height, the base length was delta xi, and the height of the rectangle was f of xi star. And these rectangles were supposed to approximate the area above the interval xi minus 1 comma xi, which is below the graph of f. And then as we summed it up, this would, the idea was that this would be some approximation of the area under the graph of f, and of course, this is with f positive. If f was negative, then this would be the same thing, but on the other side it would be the area above the graph of f, except that in that case we would be computing negative of that area. Okay. So, this was supposed to approximate that, and as we made our partitions finer and finer, the idea was that it will indeed approximate the area, and that was the definition of the definite integral of f from a to b. So, this was defined as the limit as norm p tends to 0 s of p. So, that is norm p tends to 0 summation f of xi star times delta xi, and the integral was denoted by this symbol. The leftmost sign there is called the integral. The smaller number is written on the bottom of that integral a, the larger number is written on the top, that is b, and then the function that you want to integrate is written next, and then this we have this thing called dx, which indicates many things. In particular, it indicates the end of the integral that we want to compute. So, this was the notation of the definite integral of f from a to b. Now, in the last video, I did not make clear why I called it the definite integral, and that is because in this video we are going to talk about something called the indefinite integral, and it will help us in computing this number. So, in the previous video we have seen how to integrate 2x minus 1 from 1 to 2. We saw it was a fairly non-trivial computation. We had to do some amount of work in order to get that. So, if we have more complicated functions, presumably we would have to do much more work in order to compute the integral, and that defeats the purpose of defining the integral, which is that the integral is supposed to quickly calculate these areas. So, in this video what we are going to do is we are going to link this integral with something that we have studied even before, namely the derivative, and then using that we will compute these integrals, and you will see that it becomes a very routine process once we understand how to link it up with the derivative, or rather the antiderivative. Okay. So, let us define what is an antiderivative. So, let f be a function defined from a domain D in R to R, and antiderivative of the function f is a function capital F defined on the domain D such that f prime, capital F prime of x is little f of x for all x in D. So, in particular, of course, this assumes that the function capital F is differentiable, and then when we compute its derivative, that is little f of x. So, capital F of x is the antiderivative of little f of x, right, because little f of x is the derivative of capital F of x. So, the antiderivative is just reversing the operation of differentiation. We are saying, well, you differentiate and you get little f of x. So, is there some function capital F of x such that when I differentiate that, I get little f of x. So, that is what we will call the antiderivative. So, just as an example, if suppose little f of x is x to the power 7 plus 2 times x to the power 6 minus pi times x to the power 5 plus 0.5 x to the power 4 minus 9, then its antiderivative is x to the power 8 by 8 plus 2 times x to the power 7 by 7 minus pi times x to the power 6 by 6 plus 0.5 times x to the power 5 by 5 minus 9 times x. If you are wondering how this came, well, take this capital F of x, differentiate it and see that you get little f of x. So, what we did is we know how to differentiate. So, we try to go the other way and ask how do I sort of undifferentiate or anti-differentiate, yeah, and that is the antiderivative. Okay. So, we will see in a few slides how to get the antiderivatives. Here is a fact: if capital F is an antiderivative of little f, then if you add a constant, so f1 of x is capital F of x plus c, where c is some real number, any real number in fact, then capital F1 of x is also an antiderivative of little f. So, how do I get that? Well, you differentiate capital F1 of x, but we know by linearity that that is the same as the derivative of capital F of x plus the derivative of the constant function c, and we know that the derivative of constants is 0. So, capital F1 prime of x is going to be capital F prime of x, which is little f of x. So, capital F1 of x is an antiderivative of little f of x. So, this fact is quite obvious. I just gave a proof. What is more remarkable is that every antiderivative actually has this form. So, once you identify one antiderivative of a function, you know all possible antiderivatives. So, if you know one antiderivative, then if you add a constant, that will be another antiderivative, and if you allow that constant to vary over the real numbers, that will give you all possible antiderivatives. So, there is no other antiderivative that is possible. So, just as an example, this example that we have here, little f of x is as we have here, capital F of x is as we have here, and if I added, let us say 5 to capital F of x, that will also be an antiderivative, or if I add minus 3000, that will also be an antiderivative. And in fact, what we are saying is, if you have some other antiderivative, then it is going to be capital F x along with some added to some constant. So, that is the only possible antiderivative for this function little f of x. Okay, so, I hope the statement is clear. So, because of this, we will use the instead of an for the antiderivative. Yeah, so when we say antiderivative, in principle it is not, at least we did not know before this that it is unique, and even if it is not unique, the only possible difference between two antiderivatives is that of a constant, and we will see that constants do not contribute for whatever we want this antiderivative for, and so we are going to say the antiderivative instead of an antiderivative. So, when we write down the integral, we will always have this plus c. Yeah, so the correct way of writing down the antiderivative of little f of x here is capital F of x is this plus, so plus c, yeah, where c is a real number, some real number. That is how any antiderivative is going to look like. So, So, we will use the instead of an when we talk about antiderivatives. Okay. So, that is fine, these are antiderivatives, but what is the connection with integrals? So, it says on top antiderivative aka indefinite integrals. Okay. So, we have talked about definite integrals, which are about, we are given 2 points a and b, and then we want to we have defined via Riemann sums what is integral a to b f of x dx. So, now we want to talk about the indefinite integral, which I am claiming is the antiderivative. So, the antiderivative for a function f is more often called the indefinite integral of f, and it is denoted by integral f of x dx. So, note here that when we have written this integral, there is no a or b here, there are no limits for this integration, and the point here is that when we do the definite integral, that is a number. So, the definite integral is a number which depends on the limits in question. So, it depends on a and b. Of course, if you change a and b, you get a different number, but once you fix a and b, it is some number, whereas the indefinite integral is just the antiderivative. So, it is not a number, it is a function. So, as an example, that is what we did in the previous slide, capital F x is the integral of little f x, okay, in terms of what we have written here. So, here this is called the indefinite integral or just the integral. When we say integral of f, we mean this function, which is the antiderivative, and again, as I said in the previous slide, I will be using the instead of an. Okay. So, let us pause for a second now and ask, there are many questions that we should ask, some in fact remaining from the previous video and some from this video. First is, let us talk about definite integrals. So, let us go back for a second and look at definite integrals. It is this limit. As we know, limits may not always exist. So, do we know the definite integral always exists? The answer is no. The definite integral may not exist. There are plenty of examples that we can talk about where the definite integral does not exist. However, if f is a continuous function from a to b, then the definite integral will exist. So, that is a fact that we have to remember. So, if f is a continuous function from a to b, then the definite integral will exist. Okay. The other point to make here is, what about antiderivatives? Do they always exist? And again, the answer is that antiderivatives may not always exist, or integrals may not always exist. But once again, if your function is nice, in particular if it is continuous, then indeed they will exist, and we will shortly see how to go about doing that. Okay. So far we have seen the following. We have seen the notion of the definite integral from a to b, we have seen the notion of an antiderivative, and now we have given it a different name and called it the integral of f. Okay. The definite integral from a to b is a number, it computes, the idea is that it computes the area below or above the curve, the graph of f, and between the axis. So, you have to of course keep track of the fact that the area comes with a minus sign if the function is below, and it comes with a positive sign if the function is above. So, that is what the definite integral does, and the indefinite integral is nothing but an antiderivative. So, it is that function such that when you differentiate it, it gives you little f of x. Okay. So, why did we call it the integral? So, of course, we are aware that there is some connection between these two, and that is explained by something called the fundamental theorem of calculus. So, the fundamental theorem of calculus is typically attributed to Newton, although it was sort of computationally known before Newton, but Newton formulated it as a theorem possibly for the first time, and that is why Newton is often credited with being one of the inventors of calculus. And when you say something is fundamental, really it means that it gives you some very deep insight into the subject, and indeed that is what this theorem does. So, what is the theorem? Suppose f is continuous on the domain D, which includes the interval a comma b, then an antiderivative for f on a comma b is given by this function. Capital F of x is integral a to x f of t dt. So, now just as a remark, since I am using capital F of x, I want to express my variable here as x, and the x appears in my integral as the upper limit. I can't use my x inside my integral as well, right. So, I have to integrate with respect to some other variable. So, I am calling that variable t, but do not get confused, this is just the same function little f. Only thing is I am calling the variable a different name. Instead of x I am calling it t, and that is because I want to use x as a variable in capital F. Okay. So, let us understand what this is saying. So, suppose f is continuous on the domain D, which includes the interval a comma b, then the first thing it is saying is that the antiderivative exists or the integral exists, and the integral is in fact given by considering the definite integral from a to x f of t dt. Now, this is of course a theoretical statement, right, because as we know the integral, the definite integral was defined by a limit, and it is kind of hard to compute. So, this is a theoretical statement saying that the antiderivative exists on a comma b. What is really useful and practically something that we are going to use soon is that if f is continuous on the domain D, which includes the interval a comma b. So, this is the second part of the theorem, the converse in some sense, and f, capital F is the indefinite integral of little f. That means f, capital F is the has the property that when you differentiate capital F you get little f, then the definite integral from a to b of little f can be computed by integral a to b f of x dx is equal to capital F of b minus capital F of a. So, now this is giving us something interesting. It is saying that to compute the integral, the definite integral from a to b, find an antiderivative or find the indefinite integral, and then evaluate that at b, subtract out that same thing evaluated at a. Okay. This is what it is telling us. So, this second form is of immense use, and this is what we are going to use in order to compute integrals. So, we will shortly do examples about this. Before we do that, here is a table of derivatives and integrals. Why do I have a table of derivatives and integrals? Well, this is what we are going to use. So, what the fundamental theorem is telling us is that if you want to find this definite integral, you better know the indefinite integral, and then once you know the indefinite integral, evaluate it at the limits b and a, and then subtract the values out, right. So, we better know these integrals. Okay. So, how do I know these integrals? Well, I am just back calculating. I know how derivatives work, and from there I am back calculating how integrals work. So, what you have to do here is you have to check out these the functions in the rightmost column, which are integrals, differentiate them and see that you get the function which is in the leftmost column. And the derivative I am just I've just written it so to jog your memory about the fact that this is something that we have actually done before. Okay. So, for the function 1, the derivative is 0 and the integral is x. How do I know that? Because if I differentiate x, then I get 1. So, the next is the function x to the power r. Its derivative we have already seen is r times x to the power r minus 1. How about its integral? Well, that depends on the value of r. If r is not equal to minus 1, then it is x to the power r plus 1 divided by r plus 1. And as you can see, if r is minus 1, then there will be a problem because the denominator is becoming 0. And indeed, when r is minus 1, you do not have a polynomial. Instead, you have log of absolute value of x. Yeah. So, in other words, if r is minus 1, then this function is 1 by x, and the integral of 1 by x is log x. So, this is something that we have seen when we did our derivatives part. Okay, the function sin x, the derivative is cosine x and its integral is minus cosine x. For cosine x, the derivative is minus sin x and its integral is sin x. For tangent of x, the derivative is secant squared of x. This is something we computed, and its integral is the natural logarithm of absolute value of secant of x. Similarly, for secant of x, its derivative is sec x tan x and its integral is logarithm of absolute value of sec x plus tan x. Yeah, and similarly we have values, we have the derivatives and integrals of the cotangent of x and the cosecant of x as given here. Now, some of these formulae in specifically these last four can be worked out from these two. Yeah, these can be obtained from here, can be obtained. And in the next video, we will do an example of this. Of course, I won't do all of them, but I will try to do at least one example. But what you can do is, you can ask, well, if I differentiate this function on the right, do I get the function on the left? That you can do by hand. Okay, so I'll encourage you to do that. Okay, to continue, let's look at the exponentials and the logarithms. If you have the function e to the power lambda x, very important function, then its derivative is lambda times e to the power lambda x, and its integral is, well, it's e to the power lambda x divided by lambda. How did I get that? We'll differentiate it and see what you get. So, some of these are, you see, some of these antiderivatives are being just obtained by observation of what the derivative function is. Okay, if you have a to the power x, then the derivative is a to the power x times log of a. Here a is of course positive, and its integral is a to the power x divided by log of a. So, again this is by observation. See that the right hand side when differentiated gives you the left hand side, and when your function is log x, its derivative is 1 by x. We have seen that few in the previous slide, and its integral is x times log x minus x. Again this is by observation. If you differentiate the right hand side, x times log x minus x, you indeed will get log of x. Okay. And here is a couple of other important or interesting functions which you may run across. So, 1 over root of a squared minus x squared, and we can write down of course what is the derivative. So, but I have not written it because it is only a tedious calculation. You can do it on your own by using the u by v rule, and then successively using that if you have composition of functions, how that behaves. Okay. So, I will encourage you to check what is the derivative of this. But what is its integral? Its integral is something interesting. It is the inverse sine of x by a. So, sine inverse of x by a. And what is 1 over a squared plus x squared? What is the integral? So, the integral is 1 over a times inverse tangent of x by a. And how about 1 over a squared minus x squared? For that the integral is 1 over 2a times natural logarithm of x plus a divided by x minus a. So, again these are all checkable. I will strongly urge you to check what is the derivative. If you differentiate the integrals, then you should get the function. Okay. So, this is just some table that is helpful. Many of these things you can derive, or some of these things you can derive on your own, but it is useful to have it in your mind so that you can quickly compute integrals and derivatives. Okay. So, let us do a couple of examples of computing definite integrals to clear our ideas about how we are going to use the fundamental theorem. So, here is integral x dx of from 1 to 2. So, let us apply the fundamental theorem of calculus. So, what I have to do is I have to find the indefinite integral, evaluate it at 2, then find the indefinite integral, evaluate it at 1, subtract that out, right. So, the way we do this is how it is written. So, the indefinite integral or the antiderivative of x is x squared by 2. So, this you can do by observation, or you can use the table that we just had, and we want to now do this from 1 to 2. So, I will write this with a bracket like this and write the 1 below and the 2 above. This is just notation. If you want to follow what we are doing, what we are saying is f of x is x, capital F of x is x squared by 2. I should evaluate f of 2 and subtract out f of 1, and that will be my answer, right. So, instead of writing these separate steps, this is how it is typically written down. So, this is x squared by 2, you put square brackets and then put 1 at the bottom and 2 at the top on the right, and then we evaluate whatever is inside the bracket at 2. So, that is 2 squared by 2, and subtract out the evaluation at 1, which is 1 squared by 2. So, this gives us 4 by 2 minus 1/2, this is 3 by 2. Okay. So, the next integral is sin x from 0 to pi. What is the antiderivative of sin x? It is minus cosine x. Now, I put my brackets, I put 0 to pi, and then I evaluate this at the limits. Now, here you have to be careful, this is a minus sign floating around. So, best to use a lot of brackets, so that you do not make any mistakes. So, this is what you get, minus cosine of pi minus cosine of 0. Okay. So, what is cosine of pi? Cosine of pi, if you remember your cosines, is minus 1. So, this is minus of minus 1, and then what is cosine of 0? That is 1. So, this is minus 1. So, what does that give us? The first thing gives us 1, the second thing gives us 1 with a plus sign, because you have a minus minus. So, this gives us 2. So, what is this telling us? This is telling us that if you take the function sin x, and if you draw that curve. So, here is the axis and here is sin x, right. So, 0 to pi. So, if you take one such thing and you ask what is the area here, well, we have just evaluated that area is 2, and now you can see the power of the integral. This area is not at all easy to compute, otherwise we would have had no real way of guessing what this area is. We would have had to maybe go through Riemann sums, get a rather difficult sum, evaluate the limit, and then get this. But the fundamental theorem of calculus tells us in one shot that the area here is 2. Wonderful. So, I will do one final example, and there is a very important reason I am doing this example. You will see examples like this in other courses, for example, in statistics, where this exponential decay will appear as what is called a density function. So, I also want to emphasize here our notations for the function and its antiderivative. The function was little f and the antiderivative was capital F, and if you go back to your statistics course, you might find a connection with things going on there. Okay. So, for the exponential decay function, well, here we have e to the power minus 2x from 0 to infinity. Okay. So, what do I mean by 0 to infinity? We have only talked about definite integrals where we have two numbers a and b, but we can also do this for 0 to infinity. So, by let me quickly emphasize what this means. So, if we want 0 to infinity f of x dx, we define this as limit of b tends to infinity integral, sorry, this is a to infinity a to b f of x dx. Okay, this is what we mean. Now, of course, within this definition there is many things involved. One is that the integral itself from a to b has to be defined, then the limit b tends to infinity, that limit of these numbers have to be defined. So, it is a fairly non-trivial definition. The good part is that you compute it in the same way. Okay. So, I am going to tell you how to compute it rather than how to how to theoretically justify all these steps. Okay. So, what I will do is I will use this definition. So, e to the power minus 2x dx. Well, we know an antiderivative for e to the power lambda x, that was e to the power lambda x by lambda. So, this is e to the power minus 2x by minus 2, 0 through b. Let us evaluate that. So, we get so we can pull out our minus half. So, minus half times e to the power minus bx minus e to the power minus 0x. So, that is e to the power 0, which is minus half times, I have forgotten my limit, excuse me. So, there is a limit here. Okay. So, this is limit b tends to infinity, e to the power 0 is 1. So, I get 1 minus, I am taking the minus sign inside. So, I get 1 minus or rather half minus limit as b tends to infinity, e to the power minus bx by 2, and as x tends to infinity, we know that e to the power minus bx, sorry, not x tends to infinity, as b tends to infinity, we know that e to the power minus bx is going to tend to 0, right. So, this is going to be just half. Okay. This is how we compute e to the power minus 2x, the integral is 1/2. So, if instead of e to the power minus 2x I had 2 times e to the power minus 2x, then the integral would have been 1, and that maybe should ring a bell from your statistics course, if it has come already, or if not it will shortly come, something called the exponential random variable. Okay. So, let us quickly recall what we have done in this video. We have defined what is the antiderivative or the integral, also called the indefinite integral of a function f. When f is continuous, such a thing exists, and how do we get what it is? Well, you use the knowledge of derivatives. You know how to differentiate functions, so you can manipulate and you can get what the integrals are. And then the key point was, we can use these indefinite integrals or these antiderivatives to compute definite integrals, and this is the main thrust of the fundamental theorem of calculus, which tells us that if you want to compute the integral a to b little f of x dx, find the indefinite integral capital F and then evaluate it at b, evaluate it at a, subtract the difference. So, that is the summary of what we have done here. In the next video, we will see more examples of computing definite integrals and some rules to compute definite integrals. Since this has a connection with differentiation, it should not come as a surprise that we will be able to use the same kind of idea, the same properties that we had for derivatives, similar properties and they apply also to integrals. So, we will study that and we will use that in the computation of more integrals. Thank you.